Good evening everyone. I welcome you all to the problem solving session of NPTEL course on IC engines and gas turbines. I am Pradeev E. I am one of the TA for this course. So today I have some questions on the axial turbines and compressors, and then I will solve some problems on IC engines. So before going to today's questions, in the last week someone had some questions on the blade loading coefficient, so I thought I will just go through this and start the today's content. So blade load coefficient is generally represented by the alphabet psi, and this is represented this means this means work done by the compressor in a stage divided by half U square. So this we know that Ws is Cp into delta T naught over the stage, and you have U square in the denominator, and then this 2 comes here. And this is one way of representing the blade load coefficient. Some authors eliminate this 2 and then write it as like this. So for both the axial and centrifugal compressors, some authors use this and some authors use this. I think in this course we are following this, as I saw in week 11 lecture 3 at around 27 minutes. You can see this. Then someone had, I think Subham had a question on this velocity triangles. In the last class, by the time I explained, he was away, and I think today also he hasn't reached it. So maybe I will skip this velocity triangles and then start with today's question. So the first question is, for incompressible flow through diffuser, which of the following is right? Pressure always increases but velocity remains constant. Pressure decreases when the inlet flow is supersonic. Velocity always decreases and pressure increases. Velocity increases when the inlet flow is subsonic. Can you tell the answer? Okay. The answer is velocity always increases and pressure increases. So option is answer is option 3, because if it is mentioned as the diffuser, it means that it always increases the pressure by decreasing the velocity. So for the rate of change of area will be positive or negative based on supersonic or subsonic flow. So for a subsonic flow, the diffuser will have a diverging area. So at stage 1 you can take 1 and 2, and velocity V1 will be greater than V2, whereas pressure 1 will be less than pressure 2. And similarly for supersonic flow, you can also compare the area at 1 will be less than area at 2. Whereas in case of supersonic flow, the section will have a converging area, this is 1 2, this is the direction of flow. Velocity at, again the same thing applies, velocity at 1 is greater than velocity at 2, pressure 1 is less than pressure 2, but area at 1 is greater than area at 2. So this is the case with the diffuser, and in case of nozzle the things will be reversed. For a subsonic flow nozzle the area will be converging, and for a supersonic nozzle the area will be diverging. Which one is correct for the fluid flow through divergent passage? Always behaves as diffuser, always behaves as nozzle if the inlet flow is subsonic, only act as diffuser if the inlet flow is supersonic. It acts as both nozzle or diffuser, but it depends upon inlet Mach number. Can you tell what is the correct answer?
Sir, D.
D.
It
Yes.
acts as nozzle as well as diffuser. So it depends on the inlet Mach number.
Yeah, you are right. So for a divergent section, area at 1 is less than area at 2. If the inlet is subsonic, it will act as diffuser, which means pressure at 2 will be greater than P1, whereas velocity at 2 will be less than velocity at 1. And in case of supersonic, it will be a nozzle, which means pressure at 2 will be less than pressure at 1, and velocity at 2 will be greater than velocity at 1. For supersonic flow through the nozzle, the pressure and velocity, the pressure dash and velocity dash while flowing through it. For a supersonic nozzle,
Sir, velocity will decrease.
velocity will decrease. Okay, so velocity will decrease, so then that means option 1, right? So pressure increases, velocity, no, to actually through a nozzle velocity increases, right? The term, as I said, the term nozzle always means that it converts pressure energy to velocity energy. So nozzle converts pressure head to velocity head. And a diffuser converts velocity head to pressure head in case of diffuser, but in case of a nozzle always the pressure head is converted to velocity head. So that means through a nozzle the pressure will decrease and velocity will increase. It's option 3. And the area will increase or decrease, that will depend upon the subsonic or supersonic flow. I hope it is clear, otherwise you can ask your questions now. Okay. Function of an intake of the aircraft engine is to increase kinetic head of air at the entry of engine, increase pressure head of air at the entry of engine, reduce heat losses, or increase turbine work output.
Sir, increase the pressure head.
Yeah. So in case of a Brayton cycle, we first increase the pressure of the fluid and then have a constant volume combustion and expand it and then transfer the heat of the system at constant pressure. So instead of directly using a compressor, we can also make use of the kinetic energy available in the inlet air and convert it to pressure head and then achieve this rise in pressure partially and then use a compressor later. Select the correct sentence from the following. The flow velocity along the length of the duct increases for the supersonic inlet through the converging duct. The fluid pressure along the length of duct increases for subsonic inlet through the diverging duct. The flow velocity along the length of the duct decreases for subsonic inlet through the diverging duct. The fluid pressure along the length of the duct increases for supersonic inlet through diverging duct. So maybe you can start writing in terms of variables. The flow velocity along the length increases, so that means V2 is greater than V1 for Mach number greater than 1 through diverging duct. In diverging duct means A2 is greater than A1. So when Mach number is greater than 1, diverging duct will act as a nozzle. Sorry, it is a converging duct. So converging duct means area 2 is less than A1. Converging duct, yeah. So when in a converging duct for supersonic flow, it will act as a diffuser. So for diffuser, the 2 velocity will be less than V1. So this statement is wrong. This one, the fluid pressure increases. P2 is greater than P1 for subsonic flow for Mach number less than 1 through a diverging duct. That is A2 is greater than A1. A2 is greater than A1. Subsonic flow, it will act as a diffuser. In diffuser, the pressure head will be higher at the outlet. So this is right. You can see the next one. Flow velocity along the length of the duct decreases. So V2 is less than, decreases. V2 is less than V1 for subsonic flow for M less than 1 in a convergent duct. Convergent duct means A2 is less than A1. Subsonic flow convergent duct means it will act as a nozzle. In a nozzle, V2 is greater than V1, so this is wrong. The fluid pressure along the length of the duct increases. P2 greater than P1 for supersonic flow, Mach number greater than 1 through a diverging duct. So A2 is greater than A1. For a diverging duct and Mach number greater than 1, it will act as a nozzle where the pressure head decreases. So this is wrong. So we have only one right answer. So in the sixth question is, in case of a scramjet engine, air enters from intake at supersonic or subsonic speed and encounters combustion at supersonic or subsonic speed. So for a scramjet,
Sir, intake and combustion both take place at Mach number greater than 1.
yes,
So it's supersonic.
yeah, you're right. So for a scramjet engine, intake is intake and combustion. Take place at supersonic. Mach number greater than 1, that is supersonic. So it is option A. Choose the correct area Mach number relation for varying area duct from the following, where V is velocity, dV is change in velocity, A is area of duct, dA is change in area, M is Mach number.
Option number 4.
Option 4. So here when velocity increases, we can see LHS for we can try for nozzle, subsonic nozzle. For subsonic nozzle, LHS will be greater than 1 and RHS is for option 4. D. RHS will be so for a nozzle, subsonic nozzle, we know that area will keep decreasing, so dA is negative and m square minus 1 is negative. Negative and negative it becomes positive, but still this is not right. I think option C is correct. Actually both means the same, right?
Yes, sir.
One is in denominator, other is in.
Sorry?
The C and D both are different.
How? So I write.
Both are same.
Sorry?
Both are same.
Both are same, right?
Yes, yes.
Yeah, same. Okay. So for C and D, it is same. Okay. We can just check option A. In most of the cases, if you just put this kind of LHS greater than 1, less than 1, you will be able to find the wrong answers. Okay. For option A, for subsonic flow, subsonic nozzle, dA by A, LHS is less than 1, it is negative, and we take RHS, m square minus 1 will be again negative, and dV is positive. So LHS is also less than 1, RHS is also less than 1, but still the equation is not right. Yeah. For a given reservoir temperature and pressure, the flow at the minimum cross-sectional area of the choked convergent divergent nozzle should be subsonic, sonic, supersonic or hypersonic.
Sir, in the throat, the flow should be sonic.
Yeah. For a convergent divergent nozzle, here Mach number is less than 1. At throat Mach number is equal to 1 sonic, and at the exit Mach number is at any point at this point it is Mach number greater than 1. The flow through nozzle is said to be underexpanded when the nozzle exit pressure is higher than atmospheric or ambient, or equal to ambient, lower than ambient.
Sir, higher than ambient pressure.
Yeah, it is underexpanded when it is higher than ambient pressure.
Sir, can you explain this one? I always get confused between this.
This question?
Yes, yes. This one.
Yeah, maybe you would have seen this. Nozzle pressure at throat, it will be just, so this is distance for a convergent nozzle. Initially this is pressure. Pressure will keep falling until the choke area, and then again if the back pressure is, for different back pressure you will end up at different outlet conditions. If the back pressure is sufficiently low, so P1, P2, for P2 by P1 should be can be critical pressure ratio, or it can be less than critical, more than critical pressure ratio. So if it is less than the critical pressure ratio, that means if it is more than the critical pressure ratio, so first R means choked condition. If I would write this as PR star, and actual PR is somewhere here. So if it will start expanding if the pressure at the outlet is P2 is greater than P2 star. Okay, so P2 star means choked condition, and if it is greater than P2, that means there is no sonic velocity attained at this throat area, and it will the divergence section will start acting at as a diffuser again. Sorry, it will act as a diffuser as Mach number is less than 1. Now if for some pressure ratio, like when P2 is equal to P2 star, it will start to reduce the pressure, expand, and then you will reach a stoked condition. And if it is somewhere less than this, P2 less than P2 star, this is overexpanded condition, where you have reduced the pressure less than the ambient condition, and when it is somewhere here between these 2 points, this is underexpanded.
Okay. Yeah.
Which one statement is correct about ramjet engine? Air enters into the engine with subsonic or supersonic speed and encounters subsonic or supersonic combustion.
Sir, air enters at supersonic speed and combustion takes place at subsonic speed.
Yeah. So enters at supersonic and encounters combustion at subsonic. I think we saw earlier for the scramjet, right?
Yes, sir.
Okay, just a bit. Scramjet. Scramjet is actually called supersonic combustion ramjet. Mach number greater than 1, and for scramjet also it is Mach number greater than 1, and for combustion Mach number is less than 1, and here Mach number is greater than 1, and exhaust is it's always Mach number greater than 1. So select an appropriate airflow pattern inside the gas turbine based aircraft engine.
The last one.
Intake, compressor, combustion chamber, turbine. Which one of the following is correct for the function of intake used in subsonic aircraft? Reduces the impact of shock, improves the turbine work output, raises the pressure rate of the air at the entry of the engine, raises kinetic head of the air at the entry of engine.
The third one. It's the pressure.
Yeah, raises the pressure. We have seen earlier for the Brayton cycle, the first step is to increase the pressure by compressing, then have a combustion chamber, and then expanding, and then heat outlet exhaust. So here, in order to reduce the compressor workload, we use the inlet kinetic energy to convert the pressure. Again, this is the same question. In ramjet engine, air enters from intake with subsonic or supersonic speed and undergoes combustion with subsonic or supersonic in the combustion chamber. Okay, it is supersonic speed for the intake and subsonic speed for the combustion chamber. For fluid flow through a nozzle, pressure always decreases but velocity increases. Pressure increases when inlet flow is subsonic. Velocity always increases but pressure remains constant. Velocity decreases when the inlet flow is supersonic.
A.
Yeah, option A is right. Which of the following statement is valid for a scramjet engine? Free stream subsonic or supersonic flow enters the inlet and leaves the engine at subsonic or supersonic speed. The free stream enters at supersonic flow enters the inlet, and combustion of the fuel takes place in the subsonic or supersonic flow region.
It's third one.
Option C.
Third one. C.
Yeah, C. At both inlet it is supersonic, and combustion also takes place at supersonic.
Exhaust also supersonic.
Yeah, exhaust is also supersonic, but here it is not. Here this is subsonic and supersonic. choose the appropriate sentence for fluid flow through varying area ducts. Converging duct always functions as nozzle if the intake flow is supersonic. Converging duct always functions as diffuser if the intake flow is subsonic. Diverging duct always functions as diffuser if the intake flow is supersonic. Diverging duct functions as both diffuser or nozzle. It depends on the intake Mach number.
D.
Yeah, D is right. When the inlet flow through the converging duct is supersonic, the pressure increases or decreases, while the velocity can remain constant, increase or decrease along the length of the duct.
The velocity decrease.
Converging duct, supersonic, yeah, velocity decreases, and then we have only one option, pressure increases. The flow at the minimum cross-sectional area of the choked convergent divergent nozzle should be dash for a particular reservoir temperature and pressure: subsonic, sonic, supersonic, hypersonic. So at the minimum cross-sectional area for a choked CD nozzle, the flow is sonic, sonic at the throat area. The flow through nozzle is considered to be overexpanded when the nozzle outlet pressure is higher than ambient, equal to ambient, lesser than ambient, equal to reservoir pressure. It is overexpanded It is considered overexpanded when it is less than the ambient pressure. Which of the following expression provides the correct area Mach number relationship for variable area duct?
Sir, option B.
Option B is right. Isn't it option C? Okay, next I have few problems on ice engines. If you have any questions related to this topic, you can ask, or I can move on to problems with ice engines. Okay, if there are no questions, then we'll move on to the problems. What will be the effect of the efficiency of an Otto cycle having a compression ratio of 8 if CV increases by 1.6%? So we know the relationship for Otto cycle efficiency with respect to the compression ratio R and gamma, and we need to calculate if CV, when CV increases, what will be the effect on Otto cycle efficiency. Can someone guess if it will increase or decrease? CV increases by 1.6% and Otto cycle efficiency will increase or decrease.
Sir, it will decrease, I guess.
Decrease. Okay, so we can solve and find it. So now we have this expression, and here in the expression we have gamma. So when we have we are looking only the value of CV, which goes up by 1.6%. So we will write this Otto cycle efficiency in terms of gamma. So first I would write express the relationship between gamma and CV. You know, gamma is Cp by Cv, and Cp minus Cv is R. So R is a is a constant for a particular gas or particular molecule, and Cp and Cv will depend based on the value of R. So like it is interdependent. Cp will depend on Cv and R, and the other way. So now we want only the expression between Cv and gamma. With this we can say from here I write, from here I can write Cp is equal to R plus Cv. Then putting in this equation I would get gamma is equal to R plus Cv by Cv. That is 1 plus R by Cv, so which implies gamma minus 1 is equal to R by Cv. So gamma minus 1 is what we have in the efficiency expression. So now efficiency is, we write 1 minus 1 by R power R by Cv, and efficiency minus 1 is equal to R power minus R by Cv. Now okay, it puts 1 minus efficiency, and take ln on both sides. We'll have 1 minus beta equal to minus R by Cv ln of compression ratio R. Now if we differentiate, we will have minus 1 by 1 minus eta into d eta is equal to R by Cv square ln of R into Cv dCv. Then this will become d eta by eta is equal to minus 1 minus eta by eta gamma minus 1 ln of R dCv by Cv. So to calculate the eta value, eta we know it is 1 minus 1 by R by R gamma minus 1. So that is 1 minus 1 by R is given as 8, and gamma we can take it as 1.4, so that will become 8 power 1.4. So can you calculate what is the efficiency value, base efficiency?
Sir, 57 percentage.
Yeah, it is 56.5% to be precise. So you can write it as 0.565. And now we can calculate change in efficiency. This is minus 1 minus 0.565 divided by 0.565 into 0.4 into ln of 8 into dCV by CV, which is 1.6%. So 1.6% is 1.6 by 100. So can you get this value?
Sir, minus 1.
Minus 1. Yeah, it is
Minus 0.0.
minus 0.01025,
10.
something like that. So this is minus 1.025 percentage. Yes, I think someone said in the beginning that when CV decreases, yeah, efficiency will also decrease. So that is right. So for 1.6% decrease in the CV value, the efficiency decreases by 1.025%. So alternatively, this problem can also be solved differently. Like, can you guess how we can solve in another way?
Hi.
Hello.
I solved it logically only by putting CP minus CV upon CV in place of gamma, and then actually the numerator will increase. So sorry, denominator will increase. So ultimately, it will be one minus the amount will be more than what it would be previous. So I didn't calculate anything. I just considered. Yeah,
Yeah, okay.
logic wise. Yeah.
Yes. Yeah, that is a good observation. I am asking. So now we have found that for that it is decreasing by minus 1.025%, right? By doing the derivation and everything. So without going through much of the steps, how else can we solve and get the same value or some at least similar value? This value. Okay, so efficiency for base efficiency I had 0.565, right? And this is with the assumption of when gamma is 1.4. Now I am having the new CV value, that is 1.6% increase. CV has gone up by 1.6%. So I can calculate the new gamma value, right? So I can have I had this expression. Now earlier the value of CV will be
0.7.
yeah 0.7, but it's better we do it precisely. So I think it is 0.717. So I take this expression, Cp minus Cv is R, so gamma into Cp, we also have gamma equal to Cp by Cv, so minus Cv equal to R, so gamma minus 1 into Cv is equal to R. Now Cv is equal to R by gamma minus 1. R we know it is 287 by 0.4 is so what is the CV value when we calculate by 287 by 0.4? I hope you people have a calculator handy with you and not calculating manually on this.
Seven 7.5.
Yeah, 717.5. Now if CV increases by 1.6%, then that means CV prime, I would call it CV prime, so that will be 1.101.6, right, into 1.016 into 717.5, and that would be
1147.2 joule per kg Kelvin.
1142. It is
Yes,
only
sir.
1.016 into 717.5.
Sir, why do you multiply it with 1.016?
Because it has increased by 1.6%, right? So 1 point increase by 1.6% is CV dash is equal to CV into 1 plus 1.6 by 100, right? So CV into 1.6 by 100 is 0.016, so it is 1.016. Am I right? or you say delta CV is equal to 1.6 by 100 into CV, and that is 0.016 CV. So with that, CV prime equal to older CV plus delta CV, and that will be 1.016 CV. Yeah,
728.98.
yeah. So I can approximate it to 729 joule per kg Kelvin. So this is CV prime, right? So I have CV prime, and I can calculate the eta prime. Eta prime I can get from here. Eta is equal to 1 minus r power minus r by CV minus r by CV. Now eta prime will be 1 minus 8 power minus r is 287 and CV is 729. So what is the new efficiency?
Sir, 56%.
Yeah, I think you approximated. So this exact answer is 558,976. Okay, because the total increase is only 1%, and if you approximate, then you will not get any useful result. So now the older eta was 0.565, right? And now it has become 558,976. So delta eta by eta is eta prime minus eta by eta. So that is 0.558,976 minus 0.565 divided by 0.565.
Sir, it's same. Minus 0.010.
Yeah, so minus 0.01066. So it is approximately 1.07% negative. Earlier we found it as 1 point. So when we had d eta by eta, we had minus 1.025%, and when we had delta eta by eta, we are getting minus 1.07. So we are very close to the actual value. Do you have any questions? Okay, if there are no questions, I will move on to the next problem. What will be the effect on the efficiency of a diesel cycle having a compression ratio of 20 and the cutoff ratio of 5? Cutoff ratio is 5% of the swept volume. if the CV increases by 1%, take and take CV as 0.717, R as 0.287 kilojoule per kg Kelvin. Again, can you guess what will be the effect if CV increases by 1%? T cell efficiency will increase or decrease? Again, it will only decrease, like how it occurs in the auto cycle. We can go through the expression. So now we have eta is equal to 1 minus 1 by r power gamma minus 1 by 1 by gamma into rc power gamma minus 1 by r power gamma minus 1, right? So now if we write 1 minus gamma like in the previous case, we will have we'll have 1 by r power gamma minus 1 by gamma rc power gamma minus 1 divided by r power gamma minus 1. Now if we take ln on both sides, we will have ln of 1 minus eta is equal to gamma minus 1 into minus gamma minus 1 into ln of r minus ln of gamma plus ln of rc power gamma minus 1 minus ln of r minus 1. So now we put gamma minus 1 as r by cv and we get gamma equal to 1 plus r by cv like in the previous case. Then ln of 1 minus eta is equal to minus ln of r by cv plus 1. Okay, so we have got some expression after taking ln and substituting the value of CV instead of gamma. Now if we differentiate, we will have minus t eta by eta plus r by cv square dcv divided by r by cv plus 1 minus r by cv square rc r by cv plus 1 then ln of rc dcv by rc So I would directly write the final expression. So it will be d eta by eta x Now gamma is 1.4, and we know V1 by V2, which is R, is equal to 20, and it is given V1 is equal to 20 V2. So from this we get this, and so that means swept volume is 19 V2. So swept volume is V1 minus V2, so we will get 19 V2. And V3 is, they said 0.5% of the stroke, so sorry, they said 5% of the stroke volume, so it is 0.05 into Vs plus V2, so that is 0.05 into 19 V2, this is 1.95 V2, so which implies RC is V3 by V2, which is 1.95. Now we can calculate the base efficiency. Base efficiency is 1 minus 1 by gamma 1 by R power gamma minus 1 RC power gamma minus 1 by RC minus 1. So we have 1 minus 1 by 1.4, 1 by 20 power 0.4, and then 1.95 power 1.4 minus 1, and then in the denominator 1.95 minus 1. So can you calculate the value of the efficiency? So the efficiency is 0.649 or 64.9%, and if you calculate eta by eta, you will get negative 0.565%. So that means when CV increases by 1%, the diesel efficiency decreases by minus 0.565%. Do you have any questions? If there are no questions, then we will move on to the next problem. So in the next problem, we have a petrol engine having a compression ratio of 6, which uses a fuel with calorific value of 42 megajoules per kg. The air-fuel ratio is 15:1. Pressure and temperature at the start of the suction stroke is 1 bar and 57 degrees Celsius respectively. Determine the maximum pressure in the cylinder if the index of compression is 1.3 and the specific heat or constant volume is given by Cv equal to 0.678 plus 0.00013 T, where T is in Kelvin. Compare this value with the obtained when Cv is 0.717 kilojoule per kg Kelvin. So we need to compare, we need to find the maximum pressure at the in cylinder for a given compression index, and assuming the Cv to be a variable with respect to T and Cv to be constant. Okay, so to start the problem, the first process is the isentropic compression. So that means P2 V2 power n is equal to P1 V1 power n. Okay, so P1 and V1 is known, 1 bar and 57 degrees Celsius, and P2 can be calculated. So P2 is P1 into V1 by V2 power n, and P1 is 1 bar, so it is 1 into V1 by V2 is the compression ratio, and that is 6 power n is 1.3. So P2 can be calculated. Can you calculate P2? Yeah, 10.27 bar, and now with that T2 can be calculated. So T2 is T1 into P2 V2 by P1 V1, and T1 is 57 degrees Celsius. So 57 degrees Celsius is 57 plus 273, that is 330 Kelvin, right? Yeah, 330 Kelvin. So T1 is 330 into P2 is 10.27 divided by 1, and V2 by V1 is again 6, 1 by 6. So with this T2 can be calculated.
Five six 4.8.
Yeah, 564.8 Kelvin. Now we know average temperature during combustion. this is T3 plus T2 by 2, right? This we don't know because one temperature T2 is known but T3 is not known. What is the hint for T3 is the air-fuel ratio and this calorific value is given. So we can write CV mean is equal to 0.678 plus 0.00013 into T3 plus T2 by 2. So now we assume unit quantity of air. Then Q2 to 3 per kg of air will be 42 megajoules by 15, right? So what is the value of the heat added? Yeah, 2.8 megajoules. Now we know Q23 is also, can write it as mCV mean m dot T3 minus T2, and here we know this is 1, we are assuming for unit kg of air, and on the left hand side we have writing in terms of in kilojoules, we will have 2800 equal to CV mean is 0.678 plus 0.00013 T3 plus T2. T2 is we know that it is 564.8, so I write it as 565 by 2. So this is CV mean, and then we have T3 minus T2, that is T3 minus 565. Actually we should have this m total because the heat is supplied by the fuel, so that is for 1 kg of air 1 by 15 kg of fuel is supplied, right? For 1 kg of air 1 by 15 kg of fuel is supplied. So then final mixture air will be, final mass will be 1 kg plus 1 by 15 kg, right? So this will become 16 by 15 kg, and whatever heat is added, that will go to all the 16 by 15 kg of the mixture, right? So we will have this mass term here, and then that is 16 by 15. Now we can calculate the value of T3. So can you calculate the value of T3? Oh, sorry, this cannot be. This is an uncode. Any idea how you can solve for T3? So now we will have an expression for like AT3 square plus BT3 plus C is equal to 0, and then T3 is minus B plus or minus root of B square minus 4AC by 2A, and then taking all this you can get the value of T3. So if you have a calculator like this Casio FX991MS, you can also solve this directly. You can just enter this equation and then give solve, and you might have to give an initial value, and in this case initial value you can start from this initial temperature 565 and then solve. So if you solve in either way you will end up in value 3375 Kelvin. Now P3 can be calculated. So P3 is P2 into T3 by T2. So that is 10.27 into 3375 divided by 565. So can you calculate the value of P3? the value of P3 is 61.35 bar. Now assuming constant specific heat, we will have this 2.8 into 10 power 3 is equal to 0.717 m CV into m into delta T, so that is 0.717 into 16 by 15 for the mass, and then T3 minus 565. Now T3 can be easily calculated, so that is T3 is 565 plus 2800 into 15 divided by 0.717 into 16. Can you calculate the value of T3?
Your answer is very big.
How much is it?
4226.
Yeah, that is right. 4226 Kelvin. Now we can check for the pressure value. So P3 is P2 into T3 by T2, that is P2 is 10.27 into T3 is 4226 divided by 565, right? Yes, 565. So now we can calculate the value of pressure 3.
$76.81.
Yeah, 76.81. So 76.81 bar, when we assume CV is equal to constant, and we got P3 value as 61.35 bar when CV is some variable, function of temperature. You have any questions in this question, in this problem? Nikhil Kumar has asked, please guide us how to clear objective question on gas turbine circuit. If you have questions on any particular topic, I can answer, but how to clear objective question? You have any question that had to be answered for gas turbine subject, then we can take up the question. I think Nikhil Kumar is not online anymore. So similarly, if you have any other questions that needs to be answered, we can take the question now. Otherwise, I can go on what I have planned. I think today is the last session, so and next you will have exams in 1 or 2 weeks. Yes, Nikhil, you have any particular questions about the gas turbine? Yeah, what is the question? You can also unmute yourself and talk. Or anyone else has any other question, or I can, so next for a few problems are also on ice engines. You had cast but fear of exam will clear up. You can go through the assignment problems, and you can go through the problems that is covered in that live session, and you will have the notes of all the live sessions, right, in a Google Drive. I think the 3 people are conducting live sessions, so you can go through all the 3 this PDF or the video if you have time. And I think first you can go through the PDF and see if some questions you are not able to answer, then you can go to the live, you can go to that video and check for it. Otherwise, what is there to get fear? If you don't understand any particular concept or topic, then we can discuss now. If you generally say you are fearing for the exam, then this is not going to change your life or anything, right? For NPTEL, why you have to take so much pain? And is this course will be credited to your undergraduate stream, or you are taking only for your own benefit?
Only for the knowledge, sir.
Only for knowledge, yeah. Anyway. So, who answered this, Nikhil or?
No, sir. Me, Pranav.
Pranav, okay. Because this course is compulsory in our college, and can we pass on reading assignment questions? Okay, so first thing, you can go through the assignments, and second is you can go through the live session notes. So this will cover the previous year assignments also. And next you can go through the video lecture, and then this live session videos uploaded in YouTube. I hope Nikhil Kumar has access to all the notes I am talking about. Okay, which college you are from? Nikhil Kumar, may I know which college or which state you are from? Okay, if you are not comfortable answering that, it's fine. If you have any particular question, you can go through, or if you say that you don't know how to check the live session notes or previous assignments or something, then I can show you now. Okay. I'll go through all the assignments during the week. Okay, in addition to the assignments, you can also go through the live session notes. Okay. Now I hope everyone is ready to take the next problem, or if you have any other questions to clarify, we can also clarify. You are welcome, Nikhil. Okay, so in the next problem we have air-fuel ratio of a diesel engine as at 29:1. The compression ratio is 16:1, and the temperature at the end of compression is 900 Kelvin. Find at what cylinder volume the combustion is complete. Express this volume as a percentage of stroke. Assume that the combustion begins at the top dead center and takes place at a constant pressure. Take calorific value of the fuel as 42,000 kJ per kg, R as 0.287 kJ per kg Kelvin, and CV is 0.709 plus 0.000028 into temperature kJ per kg Kelvin. So they say they are mentioning some cycle like a diesel cycle where you have a compression and combustion happens at constant volume, and it starts from TDC. So that clearly says that it is similar to a diesel cycle, air standard diesel cycle, and then you will have this expansion, right? So now we want to find at what volume this combustion stops or combustion is complete. So here the intake conditions are not given, only the temperature at the end of compression is given, right? So we know CV expression is only given, so we have to find the expression for CV. CP we know that it is CV plus R, and the value of R is also given as 0.287, and CV is given as 0.709 plus 0.000028 T, and R is 0.287. So with this we can calculate the value of CP, that is 0.996 plus, I would write it is 2.8 into 10 power minus 5 T. Now you know dq is mCp dt, and q is equal to integral of 2 to 3 m. Okay, assuming we solve it for per kg of mass, then we will have Cp into dt. So Q is equal to calorific value by yeah, so this is because for 1 kg of air we will have around 1 by 30 kg of fuel going in. So the total heat added will be calorific value by 30, and then this is 42,000 by 30, so that is 1400 kilojoules per kg of air. So now Q, we also know that it is the integral, So we have 1400 is equal to integral of 2 to 3 Cp. We can write this expression 0.996 plus 2.8 into 10 power minus 5 t into dt. So here we have 0.996 t3 minus t2 plus 2.8 into 10 power minus 5 t3 square minus t2 square by 2. So 1400 is equal to 0.996 T3 minus T2 value is known, that is given as 900 Kelvin plus 2.8 into 10 power minus 5 into T3 square minus 900 square divided by 2. So with this we can calculate the value of T3, and that would be 2246.07 Kelvin. So now we know volume 3 is equal to T3 by T2 into volume 2, and that would be 2246.07 divided by 900 volume 2. So can you calculate this expression? Can you calculate this value? 2246 by 900. So this is 2.496 V2, okay. And we know Vs is equal to V1 minus V2, and that is V2 into V1 by V2 minus 1. So that is this ratio we know, V2 into R minus 1, and that is 15 V2, because R is 16 as given in the problem. Now V3 by Vs is equal to 2.496 V2 divided by 15 V2. So this is 16.64%. the V3 is the volume at the end of combustion, and that is 16.6% of the stroke volume. Do you have any questions in the problem? If there are no questions, I will move on to the next problem. So an oil engine working on the dual cycle combustion cycle has a compression ratio of 13:1. The heat supplied per kg of air is 2000 kilojoules, half of which is supplied at constant volume and the other half at constant pressure. If the temperature and pressure at the beginning of the compression are 100 degrees Celsius and 1 bar respectively, find the maximum pressure in the cycle and percentage of stroke when cutoff occurs. Assuming gamma is 1.4, R is 0.287 and CV is 0.709 plus 0.000028 into temperature. So P1 is given 1 bar and T1 is given as 100 degrees Celsius, that is 373 Kelvin. And Q input Q23, so we can draw the dual cycle. PV will have an isentropic compression 1 to 2 and then a constant volume combustion 2 to 3 and a constant pressure combustion 3 to 4, and then we have a expansion 4 to 5 and then blow by 5 to 1. So Q2 to 3 is constant volume combustion, that is heat supply per kg is half of which is supplied at constant volume, so that is 1000 kilojoules, and similarly Q3 to 4 is also another half, so that is also 1000 kilojoules. So the compression ratio is 13, that means R is equal to V1 by V2 and this is 13. So now we have P1 V1 power gamma is equal to P2 V2 power gamma. So to calculate the second pressure, P2 is equal to P1 into V1 by V2 power gamma. P1 is 1 bar and compression ratio is 13 and gamma is 1.4. So can you calculate the value of P2? is 36.26 bar. 36.26. Now to calculate the second temperature, we have T1 V1 power gamma minus 1 equal to T2 V2 power gamma minus 1. So that is T2 is equal to T1 into R power gamma minus 1. So that is 373 into 13 power 0.4. Can you find the value of T2? Okay, it is 1040.6 Kelvin. Now considering unit mass, Q23 is equal to 1000 kilojoules. This is m into CV into dt, and that is if you integrating from 2 to 3. So this is 1000 kilojoules equal to 0. Integrating from 2 to 3, 0.709 plus 0.0000282 dt. Then we have 0.709 T3 minus T2 plus 0.000028 T3 square minus T2 square by 2. We know the value of T2, so that is 0.709 T3 minus 1040.6 plus 0.00028 by 2 T3 square minus 1040.6 square. So which means the value of T3 is, can calculate to solving this, it is 2362.2 Kelvin. So now P3 is P2 into T3 by T2, that is 36.27 into 2362.2 divided by 1040.6, and that will be 82.34 bar. Now Q34 is equal to 1000 kilojoules, and so that is Q34 is also m into 3 to 4 Cp into dt, and 3 4, that is 1000 is equal to 0.996 plus 0.000028 temperature TTE integral 3 to 4. So we'll have 0.996 T4 minus T3, so T3 is now 2362.2 plus 0.000014 T4 square minus 2362.2 square. So which would give T4 value of 2830.04 Kelvin. Now we can calculate V4 equal to T4 by T3, and that is 1.198 of E3. We know Vs equal to V1 minus V3 equal to V3 into R minus 1 equal to 12 V3. So cutoff percentages V4 minus V3 by V plus into 100 plus So do you have any questions in the problem? Okay, if there are no questions, then I will close the session, and whoever is writing the exam, I say all the best and thank you for participating in this class and also in the previous classes. Yeah, thank you very much.